This is slide number 35 and I am your presenter Asloob Mudassar. Field calculation based on scalar diffraction theory. If an optical signal is considered as a wave, diffraction effects has to be taken into account when such a signal passes through diffracting apertures. Diffraction theory must be known to handle the diffracting wave problems. Two treatments for the light. Scalar treatment of light. It's simple, but the results obtained using it are approximately correct, but sometimes surprisingly accurate. Vector treatment of light. It is more rigorous and at the same time more accurate. Calculations of optical fields through diffracting apertures using scalar treatment of light will be presented here. If in the historical development of diffracted field calculations, Huygens, Fresnel, Sommerfeld, Helmholtz, Kirchhoff, Rayleigh, etc. were among the main contributors. In the development, incorrect non-physical assumptions sometimes were made, though they agreed with experimental results very accurately, were corrected by others. Scalar treatment of light. Maxwell's equations can deal with the propagation of electromagnetic waves. These are four vector equations in vacuum, which in MKS system are del cross E equals minus mu times curly H over curly T. The second equation is del cross H is equal to epsilon into curly E over curly T, and del dot E into electric field is equal to 0, and del dot H with mu is equal to 0. These are the four equations. Mu is the permeability of the medium in which the wave propagates. It is a measure of the degree of magnetization of a material in response to the applied magnetic field. Epsilon is the permittivity of the medium in which the wave propagates. It is a measure of how an electric field affects or affected by a dielectric medium. B is not a magnetic field, but in literature, B is also regarded as a magnetic field. In vacuum, B SI unit is a Tesla, denoted by capital T, and H SI unit is ampere per meter, are linearly related through physical constants, but they are different when inside and outside of a magnetic material. The use of either B or H in the above equations would not change the physics when dealing with the theory of diffraction in vacuum. E and H generally have three components. The three components of E can be denoted as Ex, Ey, Ez, and of course the time has to be there. So we can represent E in the vectorial form as in the E having three components, that is EP. P stands for three component, comma T. And similarly, H has three components, Hx, Hy, Hz, comma T. T is the time parameter that will also come with the propagation of H. So we have H represented as HP. Again, P as a subscript will stand three values of position, that is X, Y, Z, and of course T is there, where P stands for the position, that is any of the three quantities X, Y, Z. For propagation of a dielectric medium, we assume that medium is linear. That is, the superposition principle is valid. And this is what linearity we have seen in one of the previous slides. Medium is isotropic. Medium properties do not change with the change in directions of E and H. Such a medium is isotropic. Medium is homogeneous. That is, the epsilon is constant. Medium is non-dispersive. That is, epsilon is not a function of a wavelength of light. And medium is non-magnetic. That is, mu is equal to mu naught, is fixed. Let's write down an equation that describes the propagation of E only, independent of H. So we wanted to derive an equation that just involves only the electric field E, for which a well-known identity in electromagnetism is what we are using. For example, in equation 5, del cross of del cross E is equal to 1 over epsilon and del operating on del dot epsilon E minus del square E is equal to minus del square E. So this is the equation 5, a well-known in identity in electromagnetism. And here we are using equation 1 and 3 from the previous equation into equation 5. We shall obtain this equation. Minus mu into curly h over curly t of del square h is equal to minus del square E. This is equation number 6. Now we want to use equation 2 in equation 6 along with these modifications, that is mu will be modified to mu naught and square will be equal to epsilon over epsilon naught and 1 over mu naught epsilon naught will be replaced by c square, the velocity of light, the square of the velocity of light. The following simplified equation is obtained. So you see that making these changes, we can obtain the equation only in the parameter E, which is del square E minus n square over E square into curly square E over curly T square is equal to 0. You see that this equation is still in the vectorial form. And similarly, we can write a similar equation. If you see that in writing equation 7, we attempted to eliminate other parameters and just come out with only one parameter, that is the electric field. So we have obtained this equation. Similarly, if we do a procedure for the parameter H, we can obtain an identical equation in H, which is given. You see that you can compare equation 7 and 8. Only the parameter E replaced by H will give you the equation 8. Okay, to write down scalar versions of equation 7 and 8. Now you see that as told that we shall be dealing with only the scalar diffraction theory. So these are the vector equations and we have to write them in the scalar form. To write the scalar versions of equation 7 and 8, we choose u of p comma t. So p stands for the position, time is the time parameter to stand for any of the 6 components. This u now will stand for ex, ey, ez, hx, hy, and hz. So any of the these 6 parameters can be represented by the parameter u as a function of p and t. A single wave equation will serve the purpose of equation 7 and 8. So I am writing down equation number 9 in the as a function of u. So this u, as said previously, that will stand for any of these 6 components, 3 from electric field, 3 from magnetic field. So this stands for six independent equations. Equation 9 is actually 6 independent scalar wave equations, and there is no coupling between the 6 wave components. So remember that we have ignored the coupling between the components. Equation number 9 ignores the coupling between E and H and their respective components at the edges of diffracting apertures, which is a main error in the scalar theory of diffraction. So you see that here we are making one main error, that we are ignoring the coupling between E and H and their corresponding components. So it means that this is one of main error that we are introducing in our scalar diffraction theory, on which we are going to develop our theory. So this is one main error. I remember this main error, that how we shall correct this main error later on. The justification of using equation 9 is that we assume that the size of the diffracting aperture is much larger than the wavelength of light, and that the diffracting aperture is very thin, and that the coupling effect is negligibly small. So you see that we are justifying over this main error that we have made, that we have ignored the coupling between E and H and the corresponding components, and we are justifying this main error in that we are selecting an aperture that is much bigger than or larger than the wavelength of light, and that the diffracting apertures are very thin, so that we can ignore the coupling. So remember these 2 points. We shall be using such diffracting apertures throughout the rest of this course. Now you see that as we have developed this wave equation over here, equation number 9, it means that now we have to solve it. So we are going to try a solution for this wave equation, which is given over here in the form of u. So u of rt, or again, that could stand for any of the positions, that is x comma y comma z. And we have u as a function of a of r, which is amplitude, and multiplied by some sinusoidal function. So cos of kr minus omega t minus phi naught is our wave equation, is the solution, that is the proposed solution that we should try to come to satisfy our wave equation. A monochromatic scalar wave, which is this, you see that we are using only omega, which is 2 pi nu, and the k is only 1. This is 2 pi over lambda, so it means that we are talking about in perfect scalar domain, in perfect monochromatic scalar wave. So this is monochromatic wave equation, and this is the general solution of equation number 9. Rather than writing this solution, general solution, in the form of cos, we would prefer to write down in the exponential form, because it is easier to handle the exponential form of the wave equation. So let's do. In another form, u of pt can be written as a of p into cos of omega t plus phi. So we are introducing phi of p. Phi of p, what is the phi of p? Phi of p is equal to phi naught minus kr. So this is what we have introduced. So you see that cos is an even function. If you multiply within the argument by -1, that would not change the physics. So we have introduced phi of p is equal to phi naught minus kr. A of p is the amplitude at position p, and phi of p is equal to phi naught minus kr is the phase at position p. And here we have omega. You know that omega is the wave number 2 pi nu, where nu is the optical frequency of the wave. Okay. Representation of a wave in exponential form is easier to handle. So we can write u of a pt is equal to, we are talking about here the real part of what of this argument within the curly brackets, that is a of a t into e to the power minus iota, within the parenthesis we have omega t plus phi of t. So if you consider the real part of this, the first line, you will get the same equation that we have started in terms of the cosine functions. So again, you see that here we can split the exponential part into two parts, e to the power minus iota phi of p, and then we can separate out e to the power minus iota omega t. And we can write u of p in the third step, capital U of p. In the third step, replacing a of p into e to the power minus iota phi of p. So these two terms have been replaced by the single u of p, and then we have the time dependent function, which is e to the power minus iota omega t, is on the separate side. So again, we are remember that we are considering the real part of this one. So if we are not writing the real part as we have done in the fourth step, we shall keep in our mind that we are always talking about the real part of this, the step given in the fourth row. That is u of pt then will become equal to capital of u of p into e to the power minus omega t. So I have written the bracket that the real part is considered of the equation number 10. Now we can write that u of p on the right hand side. See that we have written that u of p is equal to a of p into e to the power minus iota into phi of p is called the phasor of the wave. So this is the phasor of the wave, that is the part of the wave that is independent of time. So we regard such part of the wave as the phasor of the wave. The real part of u of pt is equal to u of p into e to the power minus iota omega t. The real part of this quantity will represent the real disturbance. You know that a real disturbance means a real wave. If u of p U of pt stands for the physical wave, then it must satisfy equation number 9. So rather than using a equation, the previous equation, that is the equation in terms of cosine like this one or this one, we have transformed this into the exponential form, and in the exponential form we have come out with this form. So we shall be using this equation in order to satisfy the wave equation that we have in equation number 9, that is this one. So we are putting the value of u in the exponential form in equation number 9. So let's see what do we get over here. So when this equation, when this is substituted, that u of pt is equal to capital U of p into e to the power minus iota omega t in equation number 9, we have given this step in equation 11. So we can come out with some common quantities, and we can write, we can disregard some time dependent functions, because after solving them we have exponential in time that we can set to, we can omit that function, and we have del square plus n square over c square omega square, and whole within the bracket, and on the right hand side we have capital U, and that equation is equal to 0. So again, you know that we can introduce n square over c square by the term k square. So in equation 13, we have written del square plus k square, and multiplying to the operating on capital Q is equal to 0. So this equation 13 is known as the Helmholtz wave equation, very important equation, because this is the same equation that we have we derived from equation number 9, and we have come up with this equation, very important equation, Helmholtz wave equation, and it deals only the special part of a physical wave. And you see that here we have in driving equation 13 from equation number 12, we have used the dispersion relation, that is omega is equal to V, K is equal to C over N into K, was used in the derivation of equation number 13. So this Helmholtz equation we shall be repeatedly using, and our scalar diffraction theory will be based on equation number 13. So we should ignore the rest of the equations, that is from equation number 1 to equation number 12. We shall not incorporate those equations in the rest of our calculations, and the only equation that we shall be using is equation number 13. So here you know that this is the end of slide number 13. So this is the end of slide number 35.